Recording button going. There we are. We're rolling. So I believe where we left off last time was we were talking about the phrase system dynamics modeling, and we were breaking it apart and looking at the individual terms, right? So complex systems, we looked at that. Modeling, why do we model? What does Forrester say we should model? Why does Sturman say? And that leaves us dynamics. So we'll pick up the conversation there. Let's see. And so let me make sure I can share my screen properly here. All right, there we are. Okay. So I've probably said it 50 times in here already. Here comes Ashley, I guess. That we, in system dynamics, we don't model systems. We model problems from a systems perspective, right? We're not trying to make a digital twin of the real world. We're trying to simplify things, right? Find out what's important to a particular problem and include that, and then exclude all the other stuff, right? Hey, Ashley. How are you? We just began, so you didn't miss any of the important stuff we were talking about.
Okay.
Riding amusement park rides in the rain and how that's not a good idea.
Yeah. All right, great. Sorry about that. I get home right at this time, so it's always a little tricky getting on right at 6.
Yeah, no problem. In fact, that's precisely what we said, that often there's a transition going on. People are, ending one class or something and starting the next one, or they have a Zoom snafu or something. So we always give people a little wiggle room.
Thank you.
So yeah, no problem. So at any rate, so we're, system dynamics modeling, we're going to talk about dynamics now in terms of breaking that phrase apart. So we model problems from a systems perspective. So, how do we do that? Do we have any teachable, repeatable method for, having a successful modeling intervention? And the answer, of course, is yes. So we'll try and convey that to everybody today. So thinking dynamically for us means thinking in terms of what we call reference modes, okay? So what we do is we start with a precise definition of the problem, or sometimes not a problem. It could be a curiosity, something we don't understand or what have you, but it's often a problem. And we ask people to tell us what it is or write it down in words. So ideally in one sentence, tell me what the problem is, what the question is, what the curiosity is, what don't you understand? What is the thing that's motivating the modeling study, right? And you always want to circle back to that statement. It helps with guidance as to what we include in the model and what we leave out of the model, right? And it helps keep people focused on what are we trying to do here. Okay, so we go with words first. And sometimes my experience is you can go into a conference room with, 7 experts and stakeholders on some issue. They do it every day, all day for 30 years. So they really know a lot about it. Their mental models are great. And they can tell you in 3 seconds what the problem is. And everybody agrees. Other times it takes 3 days to get these people to reach a consensus as to exactly why are we here, or what's the issue. So it really just depends. But we try and get people ideally in one sentence. Maybe it's 2 sentences, but in one sentence, what is the problem, the question, the curiosity, the thing that is motivating the modeling study, and can we, write it down in words? So, yeah, Najla, sure, go ahead, please.
Oh, in the process that I learned in my MBA, the design-centered entrepreneurship, it's based on a similar process, and they teach that you should state the initial problem, but then do fact finding with using quantitative data, and then go back and redefine the problem, and then find out like what's the real problem. Is that a part of this?
Well, you'll see as we go along that modeling is an iterative process. So you see when people try and diagram, like how do you do it? There's feedback loops where you go back and revisit the problem statement as you learn more,
And then
as you,
update the reference mode.
yeah, all that stuff, right? So you don't carve it in a stone. It's not just you do step A, then you go to B, then you go to C, and then when you get to Z, you got a perfect model, right?
I see.
So yeah, it's probably in
So
harmony.
hypothetically, it could be a continuous process until the problem is solved to everyone's liking.
Yeah. Well, and you'll see
That
some
you just
people.
redefine the problem and start the process all over again until it's solved.
Yeah, you'll see there have been some people who've tried to model the modeling process. That's a little weird, but you'll see that, yeah, there's this circling back thing all the time. So I think it's a similar idea. It's not terribly, unique to system dynamics, I guess. So then what do? We take the problem statement and we turn it into a dynamic picture that we call the reference mode. So the reference mode is a graph or graphs over time of the important system variables that provide a picture, a dynamic picture of the problem. Okay. We also typically try and ask people at the beginning, all right, these graphs you've drawn, these time shapes, that make a picture of the problem, a dynamic picture of the problem, what would they look like if you've solved the problem or at least made things better, right? So sometimes that's obvious. The bad thing is growing exponentially, and if you make the bad thing not grow exponentially or grow exponentially at least slower or even shrink, that's good. And other times it's not so obvious. We circle back to define what a good city is, right? Or a good product or something. There's often multiple characteristics, right? So sometimes we get into at this point defining something like a scoring metric, because you want to know when you run simulation experiments, how do you know what run, hence what policy change or changes is the best, or is better than the last one, or is solving the problem. You have to have some way of knowing that, right? Complicated time paths can often be broken down into simpler pieces or simpler time shapes. Okay, so perhaps not surprising, we try to build simple models first and complicated models second. Now, not everybody does that. Again, often people with great enthusiasm, they learn system dynamics and they're like, this is great, I can't wait to begin. And they begin building the mother of all models that can answer all questions related to some aspect of life. And their reference mode has 16 intertwined behaviors going on. And they try and get the first cut of the model to do all that stuff, to mimic all that stuff. And that's typically a very bad idea. So we try and break complicated time shapes into simpler time shapes if through the process of, defining the problem, we come up with a complicated time shape. That's often the case when you use real data, numerical data for your reference mode. Somebody will say, I have, in a spreadsheet, I have the right here. And when you plot it, you say, okay, there's a bunch of stuff going on here and we can get to it all, but let's pick one of the modes of behavior and concentrate on that and get that under control before we start blending that with other modes of behavior. Okay, so here's an example of something we did some years ago down at, I presented this at MITRE Corporation down in Virginia at their Virginia offices. It was Manassas or something, I can't remember, it was some years ago. Presented this to the intelligence community. So we had, CIA, Defense Intelligence Agency, all the, alphabet soup intelligence analysts in the room. That is a tough audience. That might be the toughest audience I've ever had. It was one of these things where you would say 3 words and then they'd interrupt you with questions and I don't understand that. Please clarify. And I could barely get through the presentation. So that was, but anyway, one of the questions they were after was, well, when we have our analysts abroad, reading newspapers and listening to the radio, listening to TV or whatever, what should they be looking for? Eavesdropping at cafes, whatever. What's important information and what isn't important information? So we were sort of noodling through how we might use system dynamics for that. But at any rate, to illustrate the idea of reference modes for that group, we came up with this example. And this gives you the sort of before and after idea. So on the top portion of the graph, and notice in this case, we didn't say what time was. Normally, part of the reference mode definition is what do we mean by time? Weeks, days, minutes, centuries, you have to kind of nail that down. But in this case, we just said it's over time. But you notice the problem is that there's this oscillation going on. The system's going up and down, right? And you see that there's the legitimate and the non-legitimate economy. This would be for a developing nation. And we would call the non-legitimate economy in the US, we call that the underground economy, typically. And that's the economic activity that takes place off the books, basically outside of government measurement. So it's either illegal activities or attempts to avoid taxes, typically. And so you see the legitimate and the non-legitimate economy are oscillating. When one is up, the other's down, and vice versa. So there's you got two states. When there's more of the one, you have less of the other, and vice versa. And then you have dissonance in the government's moral authority. So the idea is, when the government has a high rising moral authority, over here, the dissonance goes down, and vice versa. And when the government has a high moral authority, the legitimate economy, the one that's measured and taxes are paid and what have you, people are obeying the law, is high, and the underground economy is low, and vice versa. So the idea is, this is the problem. How do you stabilize that? And then here's what it would look like if the problem were solved. There's always going to be somebody opposed to something. So dissonance is not zero, but it's low and stable. The government has high moral authority. The legitimate economy is growing, and the underground economy is shrinking. Now, so this one was really, this is mainly from Khalid Saeed, who was one of our System Dynamics faculty members, and he grew up in Pakistan and then lived and taught in Thailand for quite some time. So he had quite a good mental model about living in these sorts of situations. So it was sort of this is a nice version of a hand sketch that he did. Here's something, on the other hand, that involves numerical data for a reference mode. So this is sort of mental model. This is numerical data. Now, this is, if you look here, it's from USA Today. Now, I've never subscribed to USA Today, so I have to, and this is, you can tell, is this when you actually used to get a physical newspaper. It's much rarer today. But I had to be traveling when I saw this, because a lot of times hotels would select USA Today to slide under your door in your hotel room, or have a pile of them at the free brunch in the morning, right? So I probably, you see the dates on here, it was a long time ago, I probably saw it there. But at any rate, it doesn't take a whole lot of background information or reading the article to see what the problem is here, right? These graphs tell the story very, very nicely. You have, in this case, Catholics in their population in millions growing. To my eye, it kind of looks like it's exponential. And you could say it's linear, but I think it's growing and growing exponentially, as real systems do. So there's more Catholics, but the total priests are going down. Okay. The parishes are going up, but stabilizing. But the percent of parishes without a resident priest is rising, and exponentially. And of course, if total price is going down, one of the things you'll see as we go along, among the things we'll ask is, are any of these things stocks or flows? Can we identify them? And total price, we can just ask right now, do you think that would be a stock or a flow? It's a little early in the game, but do you think that would be a bathtub or a faucet?
A stock.
Yeah, a stock, right? Total price. So it's a bathtub, and if it's going down, it means that more priests are leaving than are coming in. So look at priestly ordinations, that's creating new priests. That would be a flow, right? That would be a flow. The ordinations would be a flow into the stock of total priests. And then, if it's going down, but it's still positive, right? Ordinations, then the total priest should be rising, but at a slower rate. So there must be outflows that are bigger than the inflows. So what would be outflows from total priests? So ordinations are the inflows. You can't be a priest without being ordained, right? So that's the inflow to the stock of total priests, but the stock is going down. Ordinations are going down, but they're still positive. So the total priest should be going up, but at a slower rate. But it's going down. So there must be outflows. So what would be the outflows, do you think?
Deaths.
Okay, they can pass away.
Retirement.
Retire.
They could be defrocked.
Oh, defrocked, okay. Or I was gonna say leave the church for whatever reason, right? Stop being a priest. Okay. So here is real data from a newspaper article that was not written for the purposes of a system dynamics model. And I just happened to see it as I was probably eating my bagel one morning at whatever hotel I was at. And I said, oh, this would make a nice example, right? It's a little bit dated, but so what? But it's the idea is you can have numerical data as opposed to mental model information. Either is fine, or you can have a blending of them. Notice in this case, we have specific dates, and we're obviously in years, whereas here we were a little bit wishy-washy. It's time. Okay, so depending on that, that doesn't necessarily mean we would keep it at time. We'd probably tidy that up if we were pursuing this modeling situation here. And here we have a much more defined situation. But the takeaway here is, so there's a couple of takeaways. So you can do it with numerical information or mental information or written information, right? And you can, you want to look at not just each important variable, the time shape of each important variable, but also the time shape of each important variable in relation to each other, okay? So you'd be saying is when one is going up, is the other going down or whatever, like that's happening here, right? And then you want to note that ideally you should be able to just look at the reference mode and see what the problem is or tell the story, right? Now, I mentioned a couple of slides ago about complicated time paths can often be broken down into more simple time shapes, right, for the purposes of reference mode. So here's an example of a somewhat simple way of doing this. Sometimes you don't even have to use formal math. You can just eyeball something and say, I see there's several things happening here, and we're going to just, focus on one mode of behavior. But here's a little bit of a more formal method just to give you an idea. So here is, in my world, I'm a macro money economist. So here's the US GDP in real terms in the black line. And the red line, I fit a trend to the data. And you can see the equation for the trend is up here. It's a cubic, right? And it's got a very nice R squared. So it's a very good fit, and you can see that visually. And sometimes the economy is above trend, like during World War II, and other times it's below trend, right? But what you want to do is detrend the data, okay? So when you do that, I can, here's the data. Here's these data right here. The black line detrended. So the black line here is the detrended data. And I remove basically the cubic part of the data. And then I ran a moving average. The red line is a moving average through it. Okay. Now you could say, I'm interested in explaining the red line, that there's this longer term sort of oscillation in the data, so World War II into the 1970s, here's your OPEC oil embargoes and whatever. And then here's the sort of the turn of the century. And then we've gone downhill again. Okay. You could say that's what I'm interested in. Or you could use quarterly data. So this was annual data. This is quarterly data. I don't know how much you know about macroeconomics or macro data, but it confuses everybody because macroeconomic data is typically released quarterly, sometimes monthly, sometimes weekly, but it's most commonly quarterly data, then maybe monthly data, and then they annualize it typically. So GDP is an example of the measurement of all the final goods and services produced in the economy quarterly, sold in a market, not resold. Okay, so it's basically the size of the economy in terms of stuff that's been produced. And it comes out monthly, but it's a quarterly measure. So people are like, I don't like what's going on? And what happens is in January of every year, the Commerce Department puts out the first estimate of the last quarter's GDP. So the fourth quarter of the preceding year, the first guesstimate of what it was comes out in January. In February, the first revision to the January number, which is the fourth quarter's GDP, comes out. And then in March, the second and final revision to the fourth quarter of the preceding year comes out, and that goes in the record books. So it comes out monthly, but it's a quarterly measure, but then they annualize it. So people are all confused as to exactly what the heck is going on here. But having said that, here's the quarterly data, and I did the same thing. And you can, detrend it and fit a moving average through it if you want. Okay, there's no one right way to do it, is what I'm getting at. Is that the thing you want to do, or is that the thing you want to do? I mean, either case, you kind of get the same answer, but look at this. You might say, when I look at this, I kind of see more oscillations going on there, eyeballing it. Now, if it's just you, it's like, well, what do you want to do? But if you're working with some people, they might have an opinion as to what really is the problem. And if it's this, then you've got to smooth it a little more quickly, right? In this case, again, we would be after the red line. That would be our reference mode, right? So again, there's not one, it's not like a theorem that holds in all cases, like E equals MC squared or something like that. It's a subjective thing as to, because here we have, but you have real data, but you can play around with it all different ways. So it really depends on what you're interested in learning about. All right, so in order to get a handle on these reference modes and specifying these reference modes, because you could put your pencil or pen on a Cartesian plane on a graph and draw an infinite number of continuous curves, right? Theoretically. So, well, how do you, it's infinite. How do you deal with it? Well, we try to identify families of time shapes and relate those to our reference modes. So the first family is the linear family. Linear growth, linear decline, and equilibrium. So equilibrium, let's start there. That's really boring because everything over time is a horizontal line because there's no pressure for change. All of the inflows, the sum of all the inflows to each stock is balanced by the sum of all the outflows from each stock. So on net, the stock is not changing. It can change in terms of its contents. You know, if you have 100 U.S. senators, this is Sturman's example, and there's an election, it might be different people in the stock, but it's still 100 senators. it's unchanging, right? So equilibrium is not something you would see from a real living system. However, it's a very useful reference point. So we often put our models into equilibrium in system dynamics, then shock it out. So that's a very useful thing, particularly when we're building our models, because anything after you shock it, anything that's not a horizontal line must be the response of the system to the shock as it's digesting the shock. What is it doing? Linear growth and linear decline, on the other hand, are really not characteristics of actual living systems. Yet, most people, including highly educated people, if you ask them, draw me a graph of how something is growing or shrinking, they'll draw you a straight line. Okay. Now, it's not that they're stupid, because they're typically not taught this stuff. But moreover, look down here. We have real data here. This is data from the federal government of the United States on Medicare costs as they were projected in the mid-60s when the program was created. So the lime green line is what the government thought the cost of Medicare would be, and the red line is what it actually was. So this is kind of like Malthus, right? Food growing linearly and population growing exponentially. But if you look for the first 3 or 4 years of the projection, it actually wasn't so bad. In fact, if you take some of these pieces of the graph, you'd say it kind of looks like a line, right? So, you know, the fact that people see lines and think about lines is not necessarily, you know, shocking, you know, for a lot of different reasons. But it makes a big difference. Real systems with feedback in them do not grow or decline linearly. They grow and decline exponentially. And there's a big difference. So if one of the things that Forrester would always say to us is that he went to a reunion or an alumni thing at one point and was talking to some guy, and the guy said, oh, you know, you were my teacher 30 years ago or something. I took a system dynamics class from you. And the guy said, Forrester said, the guy said, I don't remember anything about system dynamics really, but all the details of the equations and whatever, but I read the newspaper differently ever since I took that course. And what Jay's meant when he would recount that story is that when you are aware of these, you know, these various families of time shapes, reference modes, and what have you, you begin to see them everywhere when you read the paper or whatever. So I typically, when I read the paper in the morning, if I see something that's a good example, I'll clip it. More recently, I read the paper on my phone, and I'll just take a screenshot of it, and then I'll use it. Now, I don't do every single one, but, you know, every once in a while I say, oh, that's a good one. I'll use that in class. So you have the simulated exponential growth over there for the exponential time family. And then we see, you know, lots of examples of exponential growth. We don't have to read every single one, but again, it doesn't take a lot of brain power to say, yeah, I see the blue line simulated line, and in the real data, you begin to see that, right? How about going the other way? You know, systems don't decline linearly either. They decline exponentially. And again, if you just are aware of these things, you begin to read the paper differently, as Forrester's former student said, you begin to see these time shapes. Okay. So in this case, it's the exponential decay is it's going to 0. This would be like this kind of time shape would be similar to or representative of, let's say, in my world, of depreciation. So plant and equipment is slowly decaying away. It's slowly becoming obsolete. It's slowly rusting away, wearing out. It could be an ice cube melting on a hot asphalt driveway somewhere. It could be the time value of an options or futures contract, which expires by a certain date. So you have its time value is going away. It could be representative of a drug inside the body. You take an aspirin or whatever pill or whatever, take a shot, whatever, and then it slowly is the body expels it through breathing and in urination and tears and sweating and all that stuff. Eventually, but it's heading to zero. Eventually, it'll all be gone. So similar to, but different from the goal-seeking family. So if you look at the goal-seeking family here, this is what I'm trying to contrast. The goal here is zero implicitly, whereas the goal here is not zero. So you can kind of, maybe it's splitting hairs because it's the same time shape, but it's just going down, but it's not going to zero. Whereas it could also be going up, right? So so this would be characteristic of a negative feedback process, where like a thermostat, where the goal is moved. You see here in the upper left, we're starting in equilibrium, like this. And then I mentioned we shock it out. So in this case, we shocked it out, and you see the characteristic time shape here, right? Seeking a goal of some sort. So sometimes the goal is obvious. Other times you have to think about it a little bit. In this case, this is an old graph you can see, but at the time, apparently NBA arenas could hold typically 16,000 people. And so the average attendance was kind of heading towards that limiting factor or that goal. And again, you can have decline, so decline not to zero or decline to zero. And again, as you are aware of this stuff, you begin to see these time shifts. Obviously, there's other stuff going on here. This is where there can be multiple modes of behavior. And sometimes you need formal techniques like detrending, like I showed you. And other times you can say, well, yeah, I see there's an oscillation thing happening here, but I'm happy if I can get the exponential decay modeled here, right? And over here, it's much smoother, right? Oscillation family. So systems go up and down, and they can be everything from economic systems, economies go up and down, or your heartbeat can be an oscillatory process, or oscillations in the human body in general. It can be neckties, men's neckties, the widths go wider, narrower, wider, narrower. Skirt lengths, lapel sizes, so fashions can have these things. All sorts of systems oscillate. In fact, that might be the most common behavior in the world. It's kind of hard to say what is for sure, but it's certainly very common. So what do we mean by oscillations? Well, they can be sustained, meaning they're kind of constant. Now, I've drawn this kind of as a sine wave here, but they can be regular, but they don't have to be like a perfect, a sine wave. These are sort of a stylized or idealized concepts of the different kinds of time shapes in the oscillation family. But you can have a damped oscillation, you can have an exploding oscillation, and you can have chaos over here. Now, what happens is you're going to see as we go along, from a system dynamics point of view, systems oscillate due to negative feedback. So let's back up here. The goal-seeking family, that's due to negative feedback as well. And in fact, we said that's dropping to some non-zero goal, and this is going to a zero goal. So anytime we have target or desired or goal, those phrases, think negative feedback loop. Okay, so the goal can be a human decision. I would like to have 57 employees in my department for whatever reasons, or our target market share or share price is this, and we're going to make these changes to try and hit that target, or my sales target is for this quarter is what have you. Or it could be set by biology. The human body has on average a set point of 98.6 degrees Fahrenheit, right? And the body tries to keep it there. It's not a conscious decision. You don't think, I want my temperature to be 98.6. But what happens is if you go outside on a super hot day, what happens? You begin to perspire because the body is trying to cool you to keep you at 98.6. And if you do the ice bucket challenge, or more recently, you see these people doing the cold plunges where they go into the ice tubs. I don't know if you've seen these on YouTube. Apparently, the latest rage to make yourself robust, there's allegedly health benefits and whatever, is you sit in a ice tub for like 3 minutes, and it requires mental discipline, and it's good for the body and circulate, whatever. But anyway, when you get very cold, what do? You shiver, right? In the body's attempt to warm itself up. So it can be a conscious goal for a negative loop, or a biologically determined goal. A swinging pendulum is seeking a goal of hanging straight down. That's due to gravity. So it can be a physical thing. It can be a mechanical thing. You have a thermostat or a cruise control or a guidance system, whatever. But anyway, so anytime you see goal seeking, whether it's explicit or implied or oscillation, think negative feedback loops. Okay, in the case of oscillation, you have to have a major negative feedback loop. We're going to get to major and minor loops as we go along. When you get into this sort of thing, you have minor negative loops. The difference is a major loop has more than one stock in it. Minor loops have only one stock. Okay, so the oscillation occurs because the additional stocks cause delays in the system. So more specifically, you have the primary stock, which is the state of the system, and then you have a goal for it. And if a gap opens up between what you want in that stock and what is in that stock, corrective action is motivated. But if the corrective action is delayed by other stocks, then by the time the corrective action arrives, it's no longer the right amount. It's too much or too little. So you can over and undershoot the target. So if it's a sustained oscillator, the system never figures it out. If it's damped, every time you go around the loop, it gets better and it corrects the error more and more, and you get to where you want to be, to the target. If you have an exploding oscillation, you have perverse information that's causing the feedback of information to be worse every time. It keeps giving you the wrong information and it's making it worse. And if you see an exploding oscillation, one of two things is going to happen. Either the system is going to kill itself. So think of an airplane wing that's, I don't know if you've ever flown on a plane and you look out, well, you're in the Air Force, actually, you look out the window and the wing is doing this, right? Now it's designed to do that. But if the wing starts doing at some point, no good, right? Or a machine starts shaking and at some point it's going to throw itself off of its footings, that kind of thing.
You don't want to see that.
So, sorry?
I said you don't want to see that when you're.
Yeah, exactly right. Absolutely. So an exploding oscillation is either the system's going to kill itself or it's heading to a floor and a ceiling. And then it'll bump its head and feet on the floor and ceiling and become a sustained oscillator. Okay. So that's called a limit cycle. We'll get in more of these later on. This is just the basic time shifts. And then chaos is very interesting. I don't know if anybody's ever heard of chaos. You might have heard of the butterfly effect. That's sort of common. There's actually a movie by that name with, I believe, Ashton Kutcher stars in that movie. The butterfly effect is a butterfly flapping its wings in Brazil can cause a tornado in Texas. And what that means is chaotic systems have sensitive dependence on initial conditions. And when we get to oscillation, we'll build some chaos models so you can see how it works, but it's really quite interesting. So with a chaotic oscillation, as you see down here, even though it kind of looks like the oscillation is repeating, it never exactly repeats. So like a sustained oscillator constantly is repeating, the chaotic signal never repeats. The numbers that are being plotted there, these, there's ordered pairs, there's numbers being plotted. If you were to take them for a chaotic signal and apply tests for randomness to them, they would pass most tests for randomness, even though there's no randomness in the system. It's deterministic chaos, not stochastic. It's not coming from a stochastic model. There's no probability distribution throwing randomness into the system. It's completely deterministic, but it behaves essentially randomly. And this sensitive dependence on initial conditions, think about the bathtubs, the stocks, and you have to tell Stella how much stuff is in each of the bathtubs at time 0, so it knows where to begin, right? It might be nothing's in the stock, but you got to tell it that. So the best way to tell you about the sensitive dependence on initial conditions, the butterfly effect, is to give you a little thought experiment. So, and we'll literally do this later in the course. We're not going to do it right now, but here's the thought experiment: is if you would build a model that can behave chaotically, okay, but then pretend that model is the real world. It's not, it's a model, but let's pretend it's the real world. Then let's select it, copy and paste it, and have the copy of that model, which is we're now calling the real world, be the model of the real world. So we have two identical things: the original model, which we're calling the real world, and an exact copy, which we're calling a model of the real world. It's a pretty good model of the real world, right? Because it's an exact copy. It is a digital twin, which is what we're not doing, right, in system dynamics. So far, so good. Yeah, you can imagine this. Like I said, we will literally do this later in the course, but for now. Then you say, and this only works if the oscillation is chaotic. Take one of the stocks in the model and change its initial value by epsilon, where epsilon's a really, really, really small number. And then simulate both the model and the real world together on the same graph, on the same scale. And after a little bit of time, the model, where one stock is epsilon different from the real world, and everything else is identical, it's a perfect model, won't be able to predict the real world. The trajectories will diverge exponentially. So that's the butterfly effect. Now, okay, that's kind of like fun with math or something. Why do we care? Well, the real world implication would be, if signals in real systems are chaotic, trying to build ever bigger, more detailed models to predict like stock prices or whatever it is futile, right? You can't do it, right? So I spent some time when I was much younger in Denmark in a physics laboratory where there was an SD guy named Erik Mosekilde, the Technical University of Denmark, and very nice guy. I send him a Christmas card every year to this day, and in response, he sends me reprints of his journal articles. He writes "Merry Christmas" on them. But even though he was a physicist, he was an SD guy, and his interest was he worked with physicians to try and model human body systems, but they would use animal systems. So when I was there, they were working on sheep's kidneys. And what they would do is they would model the dynamics of the sheep's renal system, and then with system dynamics. And then they would say, what if we gave it this drug, the sheep this drug, what would happen? And they would run it on the model. Then they would take a real sheep's kidney and try the drug on it and see if the model was right and whatever. So he was interested in that sort of thing. So Erik would argue, because I spent like 3 weeks there, so I spent a lot of time with him, and he gave me all his theories and whatever. He believed that all of the systems in human beings or in animals had chaotic signals like you see down here. And so first of all, he said people think that the systems don't oscillate in the body because they'll ask questions like, well, what's your blood pressure, or what's your cholesterol? Questions like that, right? And people will give you a number, right? But he would say that's the number when they took the measurement. And what he would do, he would pay graduate students, you guys are grad students, get this, to lie in a hospital bed for like 48 hours, watching TV, sleeping, reading, just lying there, pay them. But every like half hour, I think it was every half hour, they took a measurement of something. They drew blood or whatever, and they were measuring glucose or whatever he was interested in. And then they'd plot it. And you'd see whatever they were looking at was always oscillating. Right? So yeah, they took your blood pressure or your blood sugar or your cholesterol, whatever, here, and it's a one number, but it's really a dynamic thing. So he said all of the system, he believed all the systems in the human body and the animal bodies oscillated, but oscillated chaotically. And he said it's because of entrainment. So entrainment is another dynamic thing we're not talking about here. It's a much more advanced idea. But in plain English, what entrainment is, when you have oscillating systems that interact with one another. Often the interaction is not obvious. And the oscillations will entrain. So for example, in the olden days when you had pendulum clocks, I guess you still have them. Now they're more of a, cuckoo clocks and grandfather clocks are more of a novelty. In the olden days, you needed them to keep time, right? And if you went to a clock store in the morning, the proprietor would start all the pendulums swinging, give them a little shove and they start swinging, whatever. And at the end of the day, they're all entrained and swinging together. Forrester told us that at the National Bureau of Standards, before they had atomic clocks, they told that the official time for the country and whatever was determined by pendulum clocks, but they would dig down to the bedrock and embed the pendulum clocks into the bedrock at 90-degree angles to one another. And then they would take the average of however many, I don't know how many clocks there were, but they would take the average for the official time. But they would do that, embed them in the bedrock at 90-degree angles to prevent the entrainment of the pendulums, right? Because then you want the average. You don't want them all doing exactly the same thing. It's probably in a clock shop due to the vibrations, the micro vibrations on the walls that entrain the oscillations. There's been work that's been done that suggests the business cycle is each individual firm has their own oscillations, inventory adjustments, labor adjustments, but they entrain to cause the business cycle. Pinyon pine trees do this. Pinyon pines are like in the Carolinas, and they have apparently a very sweet nut that squirrels really like to eat. And so what would happen is if each year the trees would drop their nuts, the squirrels would eat them all, and the tree wouldn't reproduce. So what happens is the pinyon pines save up all their nuts and then drop them. So there's plenty for the squirrels to eat, and the tree can still reproduce. But what happens is acres and acres of pinyon pines do it together. They oscillate together. Or fireflies, they come out at twilight and they're going on and off, and at the end of the night they're entrained and doing it together. So there's got to be, how do the trees communicate? How do the fireflies communicate? How do the clocks communicate? And hence entrain is an interesting thing. But chaotic signals can't entrain. So Eric said, think about it. If all the human body and animal body systems are oscillatory, they'll entrain, and then you'll be like high as a kite and then unable to get out of bed, and then high as a kite and unable, unless they're chaotic, then they can't entrain, right? So that was an interesting theory. I don't know, I haven't talked to him in recent years. I don't know if he ever proved that theory or whatever, but that was kind of interesting. So we'll see some chaos later in the course. It's kind of an interesting phenomenon. So some real data. So again, here's the sustained oscillation that I've done, sort of stylized with no randomness. But here's some real data. This is the number of pelts of snowshoe hares turned into the Hudson Bay Company from, 1820 or something on 1940 or whatever. And there's clearly a sustained oscillation going on there. This is a very famous data set in statistics and econometrics and data science. You may or may not know this, but there are well-known data sets The IRIS data set is a famous one. For example, this is a famous one, this time series. And when somebody invents a new algorithm or statistical estimator, the referee or the editor of the journal will often say, run it on the whatever data set, and we can compare it with all the other stuff run on the same data set. Here's the Norwegian pulp industry. So we have stocks and flows here. Inventory is the stock, and then we have production and sales. Production is the inflow and sales is the outflow. And of course, when the inflow is greater than the outflow, the inventory goes up and down. And clearly the oscillation is growing, but since the Norwegian wood pulp industry still exists, I'm assuming it hit a floor and ceiling. What else did we find here? Here's seasonal fluctuations in body weight in rural Gambian women. No idea why this is happening, but I saw it and I said, oh, that's one that's kind of a sustained oscillation. And then down here we have, what, I can't remember what it is. Oh, housing inventory, new construction count in the United States. So again, there's this regular sustained thing. Other oscillatory paths, again, just in my day-to-day, whatever I'm doing, you know, I'll find them. Sunspot numbers, I'm a ham radio operator. Sunspots are good because they gin up the atmosphere and allow us to propagate our waves around the world easier. Solar flares are bad. That causes geomagnetic disruptions and lessens our ability to talk far on amateur radio. The S-shaped family. Now, we call this a family, but it's really combinations of some of the other families, okay? So here we have sort of pure S-shaped growth, but if you think about it, there's exponential growth in the first part, then there's goal seeking in the second part. So it's really a combination of, you know, this and this, right? And here's the goal, the red line. And so when you see S-shaped growth, what you'll see as we go along in the future is there has to be certain things. I mentioned with oscillation, you have to have a major feedback loop, which means there has to be a major negative feedback loop. There has to be a negative loop with more than one stock in it. And by the way, to have chaos, you need at least 3 stocks in a negative loop to get endogenous chaos. When you see S-shaped growth, you know you're going to need a positive feedback process. So that would be a bathtub making more of itself, a self-reinforcing process of some sort. People making more people, money being used to make more money, plant and equipment being used to make more plant and equipment, knowledge being used to make more knowledge. Anything that's a virtuous circle or a vicious circle. Wage price spirals. Spiral is another clue that there's probably a positive loop at work. So you need exponential growth or a positive feedback process. You need a negative feedback process that is, in this case, that is minor, so it's not causing oscillations, it's goal seeking. You need a goal or a limiting factor or a target. So that's the third thing, positive loop, negative loop, target. And then you need a non-linear relationship. Because what happens with S-shaped growth is you have a shift in feedback loop dominance. So we're going to see when we get to using Stella, we're going to look a lot at a tool called Loops That Matter. And that helps us identify when there's a shift in feedback loop dominance. With linear systems, if you set the model up where this loop is stronger than that loop, it remains so during the simulation. But if the system is nonlinear, it's possible that as the simulation unfolds, as time unfolds and the bathtubs fill and drain, the dominance of the feedback loops can change or shift. And this makes it ever more difficult to sort of mentally simulate what's going to happen in a complex system when you add feedback, shifting feedback loop dominance in there. Often, not always, when you have a shift in feedback loop dominance, you get an abrupt change in things. And abrupt changes are usually not good, right? If you're coming towards the parking lot ballard, right, protecting the building, if you're going to touch it, you want to just scooch up to ever so slightly. You don't want an abrupt change, right? So think about it. You know, if down here we have an abrupt change down here. So with situations like, let's say, climate change, a lot of times you'll hear, well, our systems can adapt. There's no need to do a crazy full court press and destroy the economy or triple people's taxes or do some extreme measures, because we'll adapt. As the seas rise around Manhattan Island, if indeed that's going to happen, what do? You just call up the Dutch and you say, what do you guys do to deal with this? And they've been dealing with it for 1,000 years. You build dikes, and they know how to do it. So you just adapt to this. So that's fine, and that's good. The risk you run is if you get these abrupt shifts in feedback loop dominance in highly nonlinear systems where there's no time to adapt. And you notice here, look with this particular time shape here. Let's say the blue line is good, something good. Wow, it's growing and growing exponentially, and it gets and then suddenly, bang, the floor falls out, and there's no time to adapt. So that's the risk you run if you say, well, we'll just adapt to whatever the challenge is. Not saying that that's true of climate change or not. I don't know what the answer is. What I'm saying is a general sort of systems principle, shifting feedback loop dominance at times can cause abrupt changes. Now here it's a smooth change, so it doesn't have to cause an abrupt change, but an abrupt change doesn't give you time to prepare, right? That's a risk you run. The mirror image, so to speak, of S-shape is reverse S-shape. Okay, so now you get declining at an increasing rate, then declining at a decreasing rate. Here you have increasing at an increasing rate and increasing at a decreasing rate. You can have overshoot and oscillate. So in this case, think of this as supply and demand. The demands on the system in blue exceed the supply of the system, which is in this case fixed. And when it exceeds the supply, the demand exceeds the supply, the result is backing off of the demands. And then when it goes below the capacity or supply of the system, it ramps up again, but eventually it gets to the equilibrium, the same place up here. It just gets there through an oscillatory process. So again, now we're combining families, right? And then, of course, you get the overshoot and collapse kind of situation, like the limits to growth, world dynamics, urban dynamics, and what have you. And in this case, the exceeding of the carrying capacity or the goal causes, unlike over here where it's constant, it causes a degradation of the carrying capacity, and that's not good. So again, if you look at data as you go along, you begin to be sensitive to this. Sometimes it's kind of subtle and sometimes it's not. Like this one over here, mailbox mania over here, very clearly an S shape, kind of looks like this, pretty smooth and straightforward. This one, is it really S shape or is it the goal seeking? But over here, just down here, you get an inflection point way at the beginning here. So sometimes it's subtle. It's a little more obvious here. Is that overshoot and oscillate? Maybe, kind of depends on, what you're interested in. Here, it's not as clean. It's a little more, it's more like this shape here, the reverse S shape in reverse, right? Here, it's a little smoother. Here, you might say, well, it's linear. Well, I see S shape over here. Maybe you don't, I mean, if you do and I don't, or I do and you don't, we got to investigate a little more. But again, you'll see multiple modes being mixed here, oscillations along with the S shape. Again, this might be more goal seeking over here. Down here, it's more, I don't know. Obviously the goal seeking is part of it. So sometimes you can't go wrong. And then you can get the overshoot and collapse You can see that in the data as well. So it just depends on, are you sensitive to it? It can be more abrupt, like up here, or gradual, right? There can be some recovery and overshoot and oscillate maybe. And, so is that overshoot and oscillate, or is that overshoot and collapse? Well, what's the problem? Are we worried about the purple, or do we care about the oscillations? Right. So then there's some overshoot and oscillations possible. Like over here, again, it looks like it's down and up. So there's some oscillation happening here. Here it's a little more obvious. Here again, is that overshoot and oscillate? To my eye, yes, but. And reverse S shape. Again, you see this in the data when you're sensitive to it. Okay. All right. Any questions? Yeah. So, Nejla, go ahead. You got a virtual hand up.
Yeah, are the S-shaped curves and oscillations and overshoot and collapse, are they all caused by combinations of the more simpler?
Yeah.
Are the
right.
first ones like building blocks of the rest?
Yeah, that's the way to think about it. Yeah. So not just me, but system dynamics teachers in general always give the caveat, is the S-shaped family really its own family, or is it really just parts of the other families cobbled together? And the answer is, kind of yes and yes. So we tend to teach it as a separate family. But yeah, the good news is you begin to see it in the data, in real data, or although people could sketch it with their mental models or whatever. But number one, and number two, we know the basic processes that cause a lot of these time shapes: a dominant positive loop, a dominant minor negative loop, a dominant major negative loop, a positive loop, a negative loop, a limiting factor, and a nonlinear relationship, and so forth. So, a limit cycle, an exploding oscillation that hits the floor and a ceiling, is a nonlinear system, right? So it's, again, we would know what to look for. It's oscillation, but it's nonlinear, and there has to be a floor and a ceiling, limiting factors. So there's some guidance that is given by studying these families as to what to do, as opposed to just looking at a blank slate and trying to figure everything out from scratch, right? Okay, so
I have a quick question. So you talked about these different, shapes that come out of kind of the, the negative feedback loops, the positive feedback loops. When you start getting into complex systems and you have multiple factors at play, do you still see a lot of these same results, or does it start to get a little more sporty when you get into multiple factors and multiple types of loops?
Yeah, so when you're looking at real data, even mental model data, it's from some complex real world system where there's a lot of stuff going on, right? And so oftentimes you have to use techniques like smoothing a data, or detrending data, even eyeballing it and saying, okay, there's several things happening here, and we don't want to address them all simultaneously. Either, you got an oscillation and growth at the same time, and you need to ask the client, which one do we want to work on here? Either you want to work on them both, then let's pick one and let's get the exponential thing figured out first. Now let's add the oscillatory behavior, or vice versa. Or they say, no, we don't really care about the oscillation. We care about the growth or decline or whatever it is. So you kind of have to ask the client what they're seeing. A lot of times you'll see too, when you do corporate stuff and you detrend the data and whatever, you'll see, like, there's other techniques other than the one I showed you, but you'll see spikes, like, and you'll say, oh, there's a sustained oscillator. Not really. You look at it as quarterly. So every time they're making their quarterly numbers, they do something, right? Deliberate. And say this is a function, sort of the accounting system. They're preparing for earnings seasons or something like that. So it just is situational dependent. And Khaled Saeed has written a paper, I think it's on our site, called Slicing a Complex Problem. And he talks about when presented with real data where there's a lot of stuff happening, how do you get a handle on, what thing are we going to work on here? You might want to read his paper and give you some additional thoughts on how to do it. And usually it's just when you do it more, it's more intuitive. You begin to just see it, where before you weren't sensitive to it before. Then when you're sensitized, you start playing around with it. You begin to see it everywhere and make suggestions to the client, like, well, you see a line, I see exponential growth. Well, what do you mean? Well, this sort of thing.
Right.
But usually you can get, with just the families I've shown you, you can pretty much get by with, and then some techniques, maybe smoothing the data, where you get by in most situations I found. You don't have to, it's really neat. You can build really complicated, interesting models with just the basic stuff, the basic building blocks. As you'll see, the basic molecules we're going to learn, the basic time shapes. They're like Lego pieces, but when you begin to connect them in different ways, you can make all sorts of interesting dynamics and address all sorts of interesting problems.
Okay.
All right.
Great.
So, all right, good questions. So we press on. So let's see next. So we're going to actually start applying, believe it or not, we're going to start applying the stuff before you know it. Again, we just want to make our way through the material in a fashion that allows us to, make sure we understand things. We don't have to rush in our case. So I feel that's a good thing. The undergraduate program is quite pressed for time. So you're like skipping a lot of stuff and really hammering people in 7 weeks, but we've got some time here to think through carefully these ideas and not necessarily rush into the model. People are always eager to model, which is cool, but we find if we take our time and really understand the concepts, that when we finally start building models, we get better results. All right, so the next stocks and flows. So we've said we don't model systems, we model problems from a systems perspective, right? How do we do that? We state the problem in words, and then we make a picture of it, which we call a reference mode. And we try to also say, if the reference mode, i.e. the problem, were fixed or made better, what would those time shapes look like? Okay. And we said that's an iterative process and what have you. So what we want to do is we want the base run of our model to mimic or look like the reference mode, look like the problem, because now we have a pattern model. Now we have an explanation for why the problem is occurring, or an answer for the curious behavior, the question, we don't understand why it's happening. Well, now we have an explanation. We don't have the explanation, we have an explanation, but presumably it's based on good mental models of people who know a lot about the system and good real data and, and best practice and what have you. All right. So the next idea is this. Well, what causes those time shapes? What causes dynamics? And the answer is that it's stocks and flows. Stocks and flows cause dynamics. So dynamics in any system are caused, or change over time in the world is caused by flows accumulating in stocks, or negative accumulating, which would be decumulation, or the stocks draining. Now, Kenneth Boulding, a very famous economist, in 1950 wrote a book where he tried to, and I have it on my shelf just over here, it's called Reconstructing Economics. And he argued in the book that economics should be redone around the concept of the balance sheet and the income statement, which are stocks and flows, that's the foundation. And this is one of his famous quotes. I still think that I was right, that economics should be built around a kind of demography of commodities with a clear distinction between the flashlight photograph, that is the population of goods at a moment of time, which is, of course, capital, and then going on from that to the movie, a succession of frames or events, which, of course, is income. So what he's saying is, think of a picture versus a video. So the video is the flow, and the picture is you stop the flow and you have a single frame, whatever frame you stop on. Okay, the freeze frame. So that's the stock. That's the state of that system at that moment in time. And then the movie or the video is the flow over time. So stocks and flows create dynamics. And he's trying to argue that that should be the organizing principle of economics. And we say that's one of the organizing principles of system dynamics. Stocks and flows create dynamics. Stocks and flows create the reference mode. So the principle of accumulation would call all dynamic and behavior in the world occurs when flows accumulate in stocks. Right. And this is from John's book, those of you who obtained a copy of it. And he says, well, there's, 4 equivalent representations of the same idea. So we use the stock flow bathtub faucet metaphor to create dynamics, right? So there's the stocks are bathtubs, right? They're also called levels. It's funny, Jay Forrester invented system dynamics, and he never called these items, these entities, stocks and flows. He always called them rates and levels. Engineers call stocks state variables because they represent the state of the system at any moment in time. So they're all synonyms. But the concept is the bathtub for the level, the stock, the state. And then the flow or the rate is the pipe and faucet assemblies that fill or drain the tubs. So here's the sort of the picture of it. And then here's the Stella version of the stocks and the flows. If you want to do math talk, what's technically going on here, you can think of it as either differential equations or integral equations. So the differential equation interpretation would be that these flow icons, I guess you would call them, represent the differential equations. Okay, or differential equation. It's the net flow. It's the inflow minus the outflow is the net flow. That's the differential equation. So it would be d stock dt is the net change in the stock. Of course, in traditional math class, you don't say d stock dt, you say like dy dt, right, in a calculus class, right? And then the integral equation version looks like this. It says the amount of stuff in the bathtub now is equal to, that's an integral symbol from calculus. What letter of the alphabet is that? Does anybody know? What does it look like? An integral symbol.
It looks like an S.
An S, yeah. So it stands for sum up. So it's in continuous time. So it's a smooth S, meaning sum up. If it's in discrete time, meaning you're jumping, I'm doing it in the front of the camera, you're jumping rather than drawing a smooth line on a graph, then the S is a sigma, it's a jagged S. And that means it's also sum up, but it's summing up discrete chunks rather than smooth or continuous chunks where you'd have a smooth S, right? So the notation here says the amount of stuff in the tub now is the summing up of the stuff that was initially in the bathtub, might be nothing, but whatever was in there to begin with, plus the inflow minus the outflow, which is what we're saying here. Okay, so 12 flowed in, 10 flowed out, so on net 2 flowed in, so you add 2 to what was ever in there before, right? Now, notice times dt. When we go a little farther down the road, you're going to see that dt is called step size in the software, and you have to specify it. So the machine is going to take discrete steps forward in simulated time. When you draw this smooth S, you're saying that you're implying that the computer is taking infinitesimally small steps forward in simulated time, and hence you're drawing sort of a smooth curve. You're never lifting your pencil off the paper when you're drawing your curve. Okay, that you're never jumping around if you're taking infinitesimally small steps. But a digital computer can't do that, right? It can take really small steps, but it runs up against round off error, right? It can't store any more places to the right of the decimal point. It can't be any more precise or small. On the other hand, if you ask it to step too big, you get integration error. So you'll see later in the course, you got to pick there's a floor and a ceiling, a round off error and integration error, and you got to pick a step size, a DT in there. But notice what's happening. You'll see as we go along, the net flow here, the inflow minus the outflow on a graph would be the flow, would be a graph of the flow. And that would be the height of the curve. And the DT would be the width of the curve or width of the step. So it would be height times width, or the area of a rectangle. So basically this calculation here is the area of a rectangle. So the computer is adding areas of rectangles to what was in the stock before. And that's how it figures out how much stuff has flowed into the tub at any given point in time. It's called Euler's method. We're going to have a whole slide deck on the details of this. So right now I'm just giving you the trailer to the movie, right? The sneak peek of what we'll see going ahead. But this is all the same idea, presented different ways. Okay, so this is my famous quote. I love this one. It was said by Joan Robinson, who is my favorite economist, and she attributed it to Michael Kalecki, an engineer who went into economics. And Kalecki is alleged to have said, "I have found out what the science of economics is. It is the science of confusing stocks with flows." Now, that's very common. People often confuse stocks and flows. They'll say deficit when they mean debt, or vice versa. The media will often do this. They'll use the terms interchangeably as though they're the same thing. But the deficit is not the debt. The deficit is a flow, the debt is a stock, right? They'll use income and wealth interchangeably. Income is a flow, wealth is a stock. Saving and savings, that one threw me as an undergraduate in my introductory econ class. To this day, I remember getting it wrong on a test. It was the only thing I got wrong, and I'm still mad to this day. I mean, like, what? What do you mean? What? Well, it's different. Saving is a flow. Savings is a stock. If you're familiar with financial statements, a P&L, or sometimes called an income statement, is flows, and the balance sheet is stocks. Okay, and the flows on the P&L directly or indirectly change the stocks on the balance sheet. Then you have your third most famous or most important statement of cash flow, which is just looking at cash coming in and out if you're using the accrual method of accounting, right? So you can know if you're staying in business or not. You'll sometimes hear people say, well, inflation is particularly now, inflation is lower, so prices have fallen. And the answer is no, inflation is a flow, changing the general level of prices. And if it's positive but lower, prices are rising just at a slower rate, not falling. Right? George Richardson, a well-known system dynamics person at SUNY Albany, State University of New York at Albany, is located quite near the state capitol. So the system dynamics group over there has done historically a lot of work with state government. They just sort of walk up the street and work in the various departments there, the students and the faculty. And George would tell the story that they went in one day to a government agency that was dealing with the homelessness problem. And they said, well, just tell us, how do you think it works? And they drew out stocks and flows based on what they were simply being told. They didn't write equations. They didn't put any feedback loops or limiting factors, any of that stuff. They just simply said, well, tell us how it works. And they just made stocks and flows based on what they were hearing. And they said it blew the socks off of all these government officials. They said, suddenly it was like the clouds lifted and explained so many different things, because they were confusing the concepts as to which was a stock, which was a flow, and policies directed at stocks are different from policies directed at flows and vice versa and so forth. And we're going to look at Jack Homer's cocaine use model here in just a minute. So some years ago, Jack Homer, a well-known SD guy, was asked to take a look at some data that the federal government had collected, survey data. And you may remember, those of us who are old enough, that I think it was the end of the Reagan administration and the start of the George Bush senior administration, they wanted to fight a war on drugs. We had a war on poverty. Now we're going to have a war on drugs. And Nancy Reagan famously said what? Her slogan was, just say no, right? So they appointed a drug czar. I think it was William Bennett, who you see frequently on morning talk shows and what have you. I think he was a BU guy at one point, but very articulate guy, smart guy. And the government said, we're wondering if we're winning the war on drugs. So let's do a survey. So they literally did this. They went out and they asked people, I'm not sure they did this to see if they're winning the war on drugs. I think they were doing the survey anyway, and then they looked at the data to see if they were winning the war on drugs. But the government would say, ding dong, hello, I'm from the federal government of the United States. Would you be a good citizen and answer some survey questions? And you would say, well, of course. The first question was, have you used cocaine in the last month? It was like the next question was, have you ever used cocaine? They didn't really ring the bell and do this. I'm making light of it, but it was an anonymous survey. It was a written survey instrument, but they did ask those questions. The data that Jack was shown was the dotted line here. That's the actual data. So this is, have you used it in the past month, cocaine? And then the dotted line here is the results over time of, have you ever used cocaine? The thinking was, well, we're winning the war on drugs. Notice the have you used in the last month thing is going down, the dotted line. And have you ever used is going down. A little blip up here, but basically it was, we're making some progress here. So not the solid lines, the dotted lines. That's what Jack was showing. And what did Jack say? People are lying in your survey. Now, of course, when you ask people sensitive personal questions, even if it's an anonymous survey, some people are going to lie because they're embarrassed, or somebody might know who I am anyway, or whatever, So I wasn't terribly shocked to hear that people lie on surveys. The government apparently was shocked. They're like, what do you mean? Because this is going to throw a monkey wrench maybe into their whole we're winning the war on drugs narrative, right? Well, Jack said, I know the difference between stocks and flows. Have you used in the last month as a flow into the accumulation, the summing up of have you ever used, right? And he said, if this dotted line is going down, but it's not zero or negative, then this cannot, the stock, which is I've ever used, can't be going down. It has to be going up at a slower rate. Unless people are dying of overdoses and are out migrating from the country. Maybe that's possible. There's an outflow here. So they said, wow, we'll hire you to do a study for us because this is like really insightful. And he said, oh, I just know stocks and flows. So Jack built a model and he tuned it up to match other data for which he was more convinced that, it was accurate data. In this case, we have a total arrests for heroin possession and the sale and manufacturer. And emergency room mentions and medical examiner mentions, these are deaths and these are overdoses, right? And projecting forward, there were some issues as to why they think it didn't project well forward, but certainly it fit the data, the past data, very well. And it fit the data very well with lying turned on. So Jack was saying, look, I'm pretty confident that these data are correct and that these data are correct. And I got my model with lying turned on to match the data. Then he said, let me turn lying off and show you what the data should have been from your survey. And here's the data with lying turned on, kind of qualitatively matching the survey data with lying turned on. And then here's it with lying turned off. That's what the data should have looked like. And here's it increasing at a decreasing rate. So it's kind of neat. In the simulated environment, you can have the underground economy as the delegitimate economies we discussed before, the stuff that by definition is not measured because you're trying to hide it from the officials for tax purposes or it's illegal. Well, you can put it in a simulation model, right? You can to have lying on and off in your model. You can, later on in the course, we'll talk a little bit about synthetic data experiments where you can see whose method of projecting the total amount of oil reserves in the United States is more accurate, the U.S. Geological Survey method or the Hubbard method. Well, you can make a system dynamics model of the oil discovery, exploration, discovery, and pumping system, and you know in the model how much oil there is to discover. And then you can code in both forecasting techniques and have each technique watch the production and discovery data and project forward, but you already know the answer because it's a modeling environment, and you can see which one can project more closely the true answer. So these are some of the advantages of the simulation world. So here's just the basic stocks and flows in Jack's model. You had the never used population, and it goes up and it goes down with population increases and deaths. Some people get initiated to cocaine use, illegal drug use. We're not yet to the feedback loop part, but think about it. How do people get introduced to heroin or cocaine or something like that? They probably don't wake up one morning and say, hey, I want to start using heroin today. They're usually introduced by somebody who's already using it, right? So think about it. When do you get a positive loop? When a bathtub makes more of itself. People make more people, plant equipment makes more plant equipment, money makes more money, drug users make more drug users, right? There'd probably be a positive feedback loop there, right? So you start using, you're an active casual user, you can become a compulsive user. You can transition out, stop using it. There's some relapse. You're a transitional user, an X user, and even X users can relapse, and then there's people pass away. When you do any of these illegal activity sorts of models, it doesn't have to be drugs. It could be gun running or something. Anything that you're trying to, there's a demand for prohibition, alcohol prohibition. Nobody's ever, as far as I know, done a system dynamics model of prohibition during the 1920s and 30s in the US and the rise of Al Capone and all that stuff. Because of it, that'd be an interesting system dynamics model. But anytime you have that sort of situation, the question is, do you fight on the supply side or do you fight on the demand side, or both? Given that you have limited resources, where do you want to deploy your resources to combat the problem? So do you want to, in the case of cocaine or heroin or whatever these, fentanyl, any of this, do you want to fight on the demand side, convincing people not to demand it or not to do it, not to use it? Or do you want to fight on the supply side, raiding the drug dens and burning the poppy fields and intercepting the cigarette boats, bringing the stuff in and whatever? So just some of the feedback loop. We haven't quite got the feedback loops yet, but since we're talking about Jack's model, so here we have the cocaine user population, kind of this, but he disaggregated into further, categories that are not shown here. But and then on the demand side, as so cocaine started apparently when they were doing this stuff in this time frame, war on drugs and all that, because it was thought to be a safe alternative to heroin. Okay. So, but as the morbidity and mortality stats started showing up, there started to be, after a delay, some perceived health risks, and that would affect the, people's desire to use the stuff. And that would change the social acceptability of the drugs. And similarly, if you're getting, it's illegal, so you're getting arrested for it, that also makes it socially less acceptable. And there's your lying that influences the lying and the reported prevalence, right? On the other hand, on the supply side, the cocaine related crimes, some addicts need the stuff, they don't have enough money, particularly if the police have been successful in seizing it, there's less of it to have, the price goes up. So they need more money to buy it. So there's more cocaine related crimes. So that affects the arrest and incarceration rate, but also law enforcement, gets into gear and they seize more of the stuff. And that influences, like I said, the price, but also the purity, importing it, and what have you. So there's all this sorts of various feedback loops. So where do you intervene with your resources?
This is a really interesting example. This is actually what I worked on in my last job at the Joint Interagency Task Force South. So we were on the disruption. We were seizing drug shipments coming from South America.
Yeah.
So we were coordinating with South and Central American countries and their law enforcement to try and get the drugs off the street.
Yeah.
But,
So you know better than me. Yeah. Go ahead. Yeah.
Yeah, no, but it's really interesting because generally speaking, depending on the administration and the political party they affiliate with, they go back and forth between focusing more on the supply side or the demand side. So Democrats tend to focus more on the demand side, and Republicans tend to focus more on the supply side for what
Okay.
we were doing more. But yeah, I mean they still haven't figured this out. They're still going back and forth every administration. And it's just fascinating to see that. But this started decades ago and it's still going on. So
Yeah. Yeah. Policy resistance and yeah. Great. Thanks for sharing that, Ashley. That's really cool. If you want to read more about the model, there's a paper in the SD Review, but there's also a chapter in Sturman's book that describes the model and the results and what have you in great detail. I might have a PDF copy of the thing. Najal, did you get a copy like from Amazon or something of the book or?
Oh, John Sturman's book.
Yeah.
Yeah, I ordered it online and I was surprised the price was so good. And then when I got it, it had a sticker that said like only for sale in like Burma and Laos and like
Oh.
I got the same thing actually.
But
Yeah,
it was a good price.
It's a pricey, brand new. It's a pricey book. Yeah, but you can find used
Speaking of
copies.
black market goods.
Yeah. So, but anyway, and there's a System Dynamics Review article, I believe, as well. But John describes the model in great detail if you want to know all the, the ins and outs of it. But
Is that the one where they found that taking drugs off the street makes crime go up?
Yeah, well, we're gonna in fact build a system dynamics model of that very thing as we go along here. So
yeah, and there would be
there's counterintuitive stuff all over the place.
There would be interesting implications for this when you tie in the policy decision to potentially legalize some of the drugs too, and what that would affect it would have on the system.
Yeah, sort of the Amsterdam approach or whatever, and
yeah,
I guess UK tried that. I don't know, maybe they still are. Yeah, so yeah, if that's an interest for somebody, that's the whole addiction. There's a system dynamics models of addiction, whether it's alcohol addiction or whatever. There are models of anorexia nervosa and bulimia, obesity. There's all sorts of psychological factors as well as caloric intake and the physical. So it just depends on what interests people, as to because there's a lot of complex systems out there. So, okay, so we'll press on. Characteristics of stocks. So we're focusing now on stocks and flows. Stocks usually change the time shapes of flows. So the integration or accumulation process changes the time shapes. Those of you who might remember your calculus, if you have a parabola or a quadratic equation here and you integrate it, you get a cubic, right? So a quadratic has one bend in it, a cubic has two bends in it. So just give you a quick idea. There's no time here, but just when I do this for this undergrads, they all often are taking calculus, so they know that one. And of course, you also perhaps remember from your calculus days, if you had them, that if you integrate e to the x, you get e to the x back plus c. So it's not an exact copy, but it's the family of time shape doesn't change. Stocks decouple flows. They make it possible for an inflow and an outflow to be different. So they create disequilibrium and they make it possible for different actors in the system to control different flows, right? So that makes it more interesting to model. And you can model with stocks and flows whatever your imagination can come up with. Now, the demographic thing is quite popular and obvious, perhaps births in, deaths out, knowledge, there's learning and forgetting, inventory, production, and sales. You have a forest, there's planting and harvesting. You can have another sort of soft variable, anger, generation and dissipation, or morale. generation and dissipation or what have you. We had this one guy, I don't know if I told you this story. Again, I don't want to repeat my stories, but he's passed away now. I'm trying to remember his name. He was a nice enough guy. He was a very smart guy. I think he's an engineer by training. And he'd always come to the SD conference every year, and he'd get on the stage for his presentation at the front of the room, and he'd turn the chair around where the back of the chair was towards the audience, and he'd kind of sit down and straddle the chair and sit down and like drape himself over the chair. And he built system dynamics models of mystic experiences. I kid you not. And they were all technically correct. And he would explain, he'd have, 30 minutes for his presentation. He'd go through the whole thing and simulating mystic experiences. And everybody would be like, okay, this is like kind of wild, but I don't know what we do with it, but but it was stocks or flow. I mean, your imagination, if you can conjure it up in your mind, in your mental model, you can and be precise about it, you can model it. Stocks create delays. This is very common, and delays are very important in complex systems, because if you remember our characteristics of complex systems, it's hard to attach or relate cause and effect when there's a big delay in between when something happens here and when it shows up here, the result shows up here. So stocks create delays. So you can see here a couple of examples that usually people can relate to. You got your rookies and your experienced employees. And this is a very common HR problem, particularly when you have, let's say, a large scale project that you're working on and you're falling behind on schedule. And you say, bring in more people to help us. Well, okay, but if these people are rookies and they don't know what's going on, what happens? Productivity actually falls, right? Worse before better, right? Because the experienced employees are pulled off of what they're doing to ramp up the new folks. And then when they get ramped up, then you get the result that you want, worse before better. You get the better part later, right? And then down here, we have just, again, depending on what's the question, how far back in your supply chain do you want to go? If you're looking at your workforce over here, we've got graduate students, college students, high school students, middle school students, grammar school students. And if you want to go before that, you got nursery school students, you got little kids who are toddlers and aren't there. You don't want to model the system, you want to model the problem. So you'd cut it off. If you think about drug dealing, and you're interdicting it, Ashley, with the military, how far back do you go? Do you go to the poppy fields or, and so forth? It depends on the scope of your model, what your problem statement is. Stocks have inertia or memory or persistence. So a stock will stay at its present level when its inflow drops to zero. That's sometimes in some circumstances called hysteresis. It's another name for that. You take the source of change away and the thing stays where it's been moved to. It doesn't go back to where it was. So, take chlorofluorocarbons in the atmosphere. 20 years ago, it was a big deal. Now it's climate change. The big deal back then was a hole in the ozone layer. And it was chlorofluorocarbons in aerosol cans, hairsprays and stuff, and deodorants and whatever, and cleaning supplies or whatever, that would go up in the atmosphere and kill ozone molecules. So in the early 90s, like 92 or something, the nations of the world signed the Montreal Protocols, which banned the production, sales, and use of CFC containing aerosol cans, aerosol products. And that was a very good thing to do, but it was a policy that addressed the flow. So there was like a little hand here that turned off this valve, but it didn't do anything to address the CFCs that were already up there. And a better model would have an outflow here, because there, again, the decay, like the ice cube melting on the asphalt, the CFCs 11 eventually break down and go away, but their half-life is very long. So they stay up there a long time, killing, ozone molecules. So, it's good to have a policy that addresses the flow. Better would be to also have a policy that addresses the stock, or the stock and the flow. or at least be cognizant that if you're doing the one, are you doing the other? Because it matters. Again, just having a basic understanding of stocks and flows. So how do we identify stocks? Well, we're going to be doing this in an exercise as we go along. And this is key because, again, like, okay, we have our reference mode. It comes from a statement. And then we made a dynamic picture of it. And we're going to be asking, well, what's causing these dynamic time shapes, stocks and flows? Well, what's a stock? What's a flow? You got to identify them. The good news is usually when you identify one, you get at least one of the other. If you identify a stock, you say to yourself, what are the flows, or what flow or flows change the stock? And you can usually figure that out. Or if you identify a flow that's important, you say, well, where does it flow to? So if you get one, you usually get at least one more, sometimes more than one more. So how do we identify stocks? It's kind of a Kenneth Boulding idea. The snapshot test down here, if you were to conceptually stop time, stop the film or the video from running, there'd be a single frame. That would be the stock. And then the flow would disappear because you've turned off the reel-to-reel movie projector, or you hit the pause button on the video. So stocks don't disappear if time is stopped, but flows do. Stocks send out signals. So it's another way to think about it. They represent the state of the system, which is why engineers call them state variables. And so in my world of economics, prices, including wage rates and interest rates, send out signals. So I would almost always model the price of something, a wage rate, and interest rate as a stock. Okay. Another way to think about it is we're going to be real persnickety about dimensioning our equations in system dynamics. We want dimensionally correct equations. And Stella will warn us if it finds some equations that are not dimensionally correct. Now, sometimes it's due to typos. You wanted to say people and you said P-E-P-L-E. You just forgot the O. You correct that. You're good to go. No problem. Other times you haven't told the software that babies are people too. So you have babies per year and you have people, and it's saying it's not right. Well, you didn't tell it that babies are people too. Other times you just have a conceptually incorrect equation and you want to tidy it up. So it helps you to think about model formulation, equation formulation, like how should I write this equation? Here's what I want it to do. Here are the inputs, and I need them to be dimensionally correct. So how do you do that? Well, stocks are measured in units and flows are measured in units per time. So if the stock is population, it would be people. And the birth rate would be people per year or people per month or babies per year, something like that. Okay. If the stock is inventory and the outflow is sales, it might be widgets per month or units per day or whatever, or canisters or storekeeper units, SKUs per month or something like that. Now it can get confusing. So watch this. So if we go to basic physics, introductory physics, this is your classical, physics 101 example where you have velocity, acceleration, and position. So think of velocity as, speed in a particular direction. So think of velocity here, velocity 2 as miles per hour in your car, miles per hour. Okay. So that would be, units per time, miles per hour is velocity. And so if you're going 60 miles per hour for 1 hour, so you're accumulating, you're filling up a tub of 60 miles per hour for 1 hour, how far have you gone? Where is your position? How far have you traveled from where you started? If you go 60 miles an hour for 1 hour.
60 miles.
60 miles from where you started, right? So you've accumulated that velocity, if you will. So velocity is clearly a flow and position is a stock. But wait a minute. What if we're looking at acceleration like meters per second, Galileo dropping the balls off the Leaning Tower of Pisa or whatever, right? Or parachuting, terminal velocity and all that, and acceleration when you jump out of the plane. So acceleration is like meters per second. So the units is meters per second is the units per time. So acceleration would be meters per second, and velocity would be, the integral of it would be meters per second or miles per hour. So velocity can be either a stock or a flow, depending on what you're doing. So it's just a facet, a feature of the technique. You say, why is it so confusing? That's gonna, well, it just is, So, it's, you could have productivity, worker productivity be widgets produced per worker per day. Okay. And then the perceived productivity by the managers, again, would be widgets produced per worker per day. And the change in the perceived productivity of the managers, the flow would be widgets produced per worker per day. So it can be, sometimes you got to noodle it through a little bit. Sometimes it's a little not obvious. You have to sort of think about it a little bit. But it still basically boils down to units and units per time. It's just, what are your units? Okay. Again, this will become clearer as we proceed here and you get more and more examples and things. Another thing we like to do in system dynamics is challenge the clouds. Go ahead, Nasia, go ahead.
Oh, what did the last part of that slide mean where it said stocks don't disappear stocks don't disappear if time is stopped?
So that's your movie thing. So your video's running and you turn it off. The video stops, the flow goes away, but there'll be one frame, like a still photo, that remains. So that would be your stock in that metaphor, I guess.
So like when you turn off the tap, that doesn't drain the bathtub.
Right. Exactly. That's a great one.
Yeah.
Right. So turning it off, stopping, because conceptually stopping time would be turn off the bathtub water or the sink flow, and the stock remains. There's still water in the dish to wash the dishes in the sink or something. Yeah. Okay. So another thing we do, and you'll even see it in the software, challenging the cloud. So we have these little things here are supposedly clouds. I'll tell you an inside story. Years ago, I don't know, at 7:55. You want to hear my story or not? At 7:55. It's okay. So years ago, in the System Dynamics summer school, they had software night, which was like the last night of the summer school, and the software vendors would come in and show the students their software packages, of course, trying to get them to adopt their software package. And one year, there was a couple of Norwegian programmers who went to Barry Richmond, who created Stella for the Macintosh, and they said, there's this new thing coming out from Microsoft called Windows. It was Windows 1. And they said, we're Windows programmers. We want to work with you to make a Stella for Windows. And Barry at the time said, this is like 1989, 1990, something like that. He said, nah, I'm going to stick with the Mac environment. And then they said to him, well, do you mind if we go ahead and do it on our own? He said, go ahead, knock yourself out. So they went and created a Windows Stella-like program, and they initially called it WinSim. Today it's known as PowerSim. Okay. And when the end of the end of the summer school one year, this is like 92, occurred, the Norwegian guys called me up because I knew them. And they said, Mike, we're in Norway, but we know the summer school is ending and they always have software night. If we send you our new PowerSim, would you show it off for us at this? Because we don't want to fly from Norway just for like a half-hour slot that we get. I said, yeah, I don't care. Sure, send it to me. So I went over to MIT and I showed it off. And it looked quite similar to Stella, but it was in Windows. When High Performance Systems, that was the company that's called IC Systems now, but it was High Performance Systems, when they found out, they went nuts. They said the Norwegian guys are plagiarizing their software. They're ripping them off. And the Norwegian guys were like, we went to you and we told you this. So it resulted in the lawyers were teed up and this whole shooting match starts, right? So Forrester says, there's not that many of us in this field. Why are you trying to kill one another? This is very bad. You will all come to me and we will resolve this in my office. So, again, the Norwegian guys go, we don't know Forrester. Would you go and see him for us first? And that's, I said, I don't want to really be in the middle of this, but I did it. And Forrester's like, why the hell are you involved in this? And I said, I don't want to be, but the Norwegian, so I kind of intervened on their behalf and I teed it all up. Anyway, they got in Forrester's office. They resolved it. Basically, Forrester said, the stocks and flows are mine. They're not Stella's. They're not, and everybody can use them. So stop quibbling. So there were a couple of changes. Everybody had to have a win. So the Norwegian guys got to do their software, but they agreed to make 2 changes to their software. Stella used to have, well, maybe it's still, I guess it still does. It has its bathtubs fill and drain animation during the simulation. And so did PowerSim. They had to take that out. So they agreed to that. And then the clouds were the same. And so the joke, it's not a joke, but they made them change. So the clouds look different in PowerSim and because they previously looked the same. And it's like they had to give Barry a win. So they take the animation and change the way the clouds look. So these things are supposedly clouds and they look different from the PowerSim clouds due to this negotiated settlement that avoided the lawsuits and everything. But at any rate, these clouds are challenged. And in the software, you can take a stock and plop it right on top of the cloud, and the cloud will go away and turn into a stock. Or you can click on the flow and pull it off the stock, and it'll go back to being a cloud. So your options are be a cloud or be a stock. It's called challenging the clouds. Now, why do you do this? So here's an example to explain why the heck this happens. Here are 2 different demographic models with different ideas behind them. In both cases, we have the Massachusetts population here, and we have in and out migration. In one case, I have clouds. The other case, I have stocks. So the way to think about the top model is that you have a fence drawn in the real world, and anything inside the fence will be in your model. That's the important stuff as defined by the reference mode. Everything outside the fence is in the real system, but it is not part of the model. It's not relevant to the problem statement. Okay? However, the fence can have holes in the fence where stuff can leave the inside of the fence and go to the environment or come inside the fence from the outside environment. So these clouds represent holes in the fence. They're technically called sources and sinks. They're sometimes called infinite sources and infinite sinks, which I don't like to say because we've just said real systems really don't have in limits of growth. You don't have stuff going to infinity. Maybe the universe does, but there's floors and ceilings. There's limiting factors. But anyway, the point is that more specifically that when people leave Massachusetts, they go through the hole in the fence and they go somewhere. They go outside of the model. The model doesn't care. In principle, any number of entities, in this case, people, I guess, can exit through the hole in the fence and the model doesn't care. That's why it's an infinite sink. Similarly, when people come into Massachusetts, where they're coming from, they come through a hole in the fence, and where they're coming from is of no interest to the model. It doesn't keep track of it. So there's no limits. If you cared, in the lower model, you replace the clouds with stock. So in this case, I just made this up. We're interested in people coming from Connecticut to Massachusetts and leaving Massachusetts going to Vermont. So now the model's going to care. It's going to keep track of these, folks. And there's limits. If this is 0, nobody else can come in, right? And if this is full, whatever, if you can fill up Vermont, I don't know what that means. But if that's full, then nobody else can leave and go to Vermont. So now limits come into play and the computer's keeping track of things and whatever. So that's what it means to challenge the clouds. if you do this kind of thing, your model will be dissipative technically in mathematics. And if you do this, it'll be Hamiltonian. So whether stuff can leave or not there are two kinds of dynamic systems in mathematics, but we don't care about that per se, the technical definitions. This is, can you go through the holes in the fence or not? I mentioned stocks and flows don't exist in isolation. They're part of feedback loops, and that we'll get into feedback loops next time, but there's major and minor loops. We talked about that in terms of oscillation and chaos and stuff. If there's only one stock in the loop, it's a minor loop, positive or negative. And if there's more than one stock, it's a major loop. So we talk a lot about major and minor loops as we go along. And then lastly, and then we'll let everybody go because we're out of time here. There's this thing called hand graphing that, like, Sturman loves doing this. I'm kind of like, a little bit indifferent to it. Let me show you, but I do it more because other people do it. So just so you're familiar with it. If you say you studied system dynamics, you want to be able to say, I know hand graphing because Redzicki taught me it. So what you do is this, and then this will be the last thing. So I guess the intention is to help people appreciate what the computer is doing on your behalf, but you make the simplest dynamic system in the world, one stock and one flow. It's technically a net flow over here, so we'll call this net flow. Usually, though, you use the term net flow when you have an inflow and an outflow, but we can also make it do this. It's called a biflow and still a net flow. Stuff can go in and out. So that's the net flow, and this is the stock. So it's the simplest dynamic system in the world. There's no feedback. There's no limiting factors, no nonlinearities, any of that stuff. And then you pose the question, look, if I show you the time shape of the net flow. So if I graph the net flow for you, and these are positive values, this is 0, and these are negative values. And let me get a different color here. If I graph the time shape for you, again, we're talking time shapes here. So if the net flow looks like that, can you tell me what the time shape of the stock is, which will be right below it? So the stock is down here, and we have 0 down here. There's some initial value here, some number there's whatever's in the stock to begin with. So we just pick an arbitrary value there. It doesn't matter what it is. So how would you determine without the computer how much stuff is in the stock? Well, what we say is, hey, if something happens, maybe I should just draw a solid line. If something happens on the net flow, run a line down to the stock. And then let's noodle through it. So in this region right here, this first region here, the net flow is 0. Nothing's going in, nothing's going out. So what would the time shape of the stock look like if nothing's going in and nothing's going out? And you're starting at some value like 5 or something here. So what would the time shape look like? Nothing's going in, nothing's going out.
It would just be flat.
Just be flat, horizontal line. So whatever's in there is in there, right? So then you ask the question, okay, now something like 3 goes in, 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 3. So what's the time shape in the next section look like here?
Linear growth.
Yeah, so it's going to grow because stuff is going in, okay? And it's always 3, so it's going to be constant. Then it goes to 0 here, so it would be the same thing as over here. All right, so we've just done an integral, believe it or not. This is essentially what the computer does for us. And we can note several things. Number one, the integration process has changed, or the stock has changed the time shape of the flow, right? The red curve on the top looks different from the red curve on the bottom, right? Stocks have momentum or memory or persistence, right? Because this is like the chlorofluorocarbon thing. We turned off the flow here and the stock did not go back to where it was, or hysteresis. It remained at the higher level, right? So we've seen some of the characteristics of stocks. We can also do a little bit more formal sort of mathy stuff here. If we were to look at this height over here, that's the amount of stuff that has flowed into the stock, right? What would be the equivalent thing on the top graph? The height on the bottom graph is what on the top graph? Think of if you've had some calculus back in the day, when you do an integral, what are you finding?
Is it the area?
The area
And the
beneath the curve. Yeah.
rectangle?
So this area here, that area is the height there, right? And one other thing we can sort of, so you can see how these things are related to one another. The slope here, you know, versus a steeper slope. You know, if this thing were steeper, what's that over here? How would that look like? What would that look like up here? So instead of 3, 3, 3, now you have 5, 5, 5. It would be higher, right? And then, of course, there would be more that flowed in and so forth, right? So, you know, you want to be able to relate the two, excuse me, the two types of graphs of flows and graphs of stocks, and see how they relate to one another. And of course, that's what the computer's doing. So, and then you begin to see the characteristics of stocks. So Sterman would, like I said, he loves these things. I'm always like, you know, all right, whatever. It's not really my thing, but the kids tell me at Tech that the physicists do this all the time. So apparently it's like, okay. And I mean, you go the other way. In his book, John goes the other way and says, if I give you the stock, can you tell me the net flow? Actually, what John does in the book, you know, maybe I should just, sorry, in the interest of time, let me clear it. What John does in the book is he gives you the inflow and the outflow, and you have to first calculate the net flow and then calculate the stock. He isn't as nice as me. But let's just do one more. And then you get to kind of get the idea. I don't necessarily want to belabor these things, but in the interest of time, I'll do them a little quicker here. But again, I give you the net flow, you know, something like that. What would the stock be? And again, if something happens, we draw a line down. So crossing the 0 line would be something happening.
So crossing the 0 line is like draining the tub.
Yeah, so this is net flow. So now, right, instead of stuff going in, stuff is going out, right? Okay, so yeah, it's a good question. So we're starting with an arbitrary amount in the tub. So in this first region here, we got 3 going in, 2 going in, 1 going in. So stuff is going in, so it must be growing, filling up. It's increasing, but at a decreasing rate. Okay, now 1 goes out, 2 goes out, 3 goes out. It's going to decrease at an increasing rate. Inflection point, 3 goes out, 2 goes out, 1 goes out. It's still draining, but it's decreasing at a decreasing rate. It's 0, inflection point. 1 goes in, 2 goes in, 3 goes in. We increase at an increasing rate. Then we're back to here. 3 goes in, 2 goes in, 1 goes in. We're increasing at a decreasing rate. And guess what? It repeats. Okay, again, we note that stocks change the time shape of flows. You know, in this case, it gets rid of the sharpness. So it attenuates, or you'll see it's a move like a moving average. It's a smooth, right? Notice over here, we got the trough here, but the trough here, we have the peak here and the peak here. So there's been what the electrical engineers call a phase shift, right? A 90-degree phase shift. You're looking at voltage and current and all that in electrical engineering. That's with the waveforms, you see these things. So stocks create delays, right? The peak and the trough happened later. Change the time, shape of flows. So you can, there's a lot of, with the hand graph, there's a lot of things you can kind of learn, right, from looking at it. And just to wrap up then, if we go to, not the feedback loop, did I? Oh, I must have closed it. If you look at the slide deck, I don't want to take the time to reopen it because we're past that. But if you look at the slide deck, I give you a more complicated one with all different stuff. And then can you, if you want to try and figure it out mentally, what the stock is doing, and then then below the next slide, it's been simulated and you can see the answer. And again, it's, to me, it's just, it's a skill to kind of look at, both the stocks and the flows. When something's happening in your model, the stocks are the state of the system and it's doing whatever. Well, why is it doing it? What are its flows and what are they doing? So to kind of relate the two is important. Excuse me. And then I think you do gain an appreciation for what the machine is doing on our behalf. Because you say to yourself, yeah, I wouldn't really want to try and do this now with nonlinearities and feedback loops and 17 of these things and whatever all happening. You really do need the machine to assist, to handle the integration. All right, any questions? Because I think Mike was running on at the mouth again, but
I don't have any questions right now.
okay. But I'm guessing most people say, okay, fairly straightforward. Like, okay, there was sophisticated stuff happening there at one level, but on the other hand, like, I get it. It's kind of, it's pretty straightforward. So I'll leave you with this. George Richardson always said, when people say, oh, bathtubs are faucets, that's just easy, he says, yeah, it's so easy until you try and do it or do it well. It's easy to do poorly. It's hard to do well. But you can notice that Forrester and et al. Did not leave us with like no guidance on how to do this stuff, right? There are well-defined ways of proceeding, of thinking about things to assist, right? Still, it requires practice and whatever, but we're not left stranded on an island by ourselves. Like, what do I do? What do I do? Right? Like, here's the software, good luck, right? So, next we'll look at feedback loops. And then we're going to start, getting the software out. We're going to read a newspaper article. We're going to start building a model of it, talking about, do you see any loops in here? I mean, it's just a newspaper. It wasn't written as the first system dynamics textbook. Some reporter wrote an article, but can you find the loops? Can you find the stocks? Can you find the flows? Are there reference modes that are possible? How do you put all that stuff into the software? So on and so forth. Okay.
All right.
Okay. So we'll leave it there. Same time next week. Email me if something's up. Otherwise, we'll see you guys.
All right. Have a good night.
You too. Bye.